All right, welcome back. Today is the 11th of February. It's lecture 10 now in week 5 of our semester. And we are going to do lab 2 and we will talk about question 3 and 5. What are questions 3 and 5 of the lab 2? Let us see. In lab 2, we are told that we have a wave file and then we have a LTI described by this. This LTI is very, very strange. It is very strange because although it has a length of 8,000, most of them are zero. Only the at time sample 1 is 1, time sample 4,000 is 0.5, time sample 7,900 is 0.3. So it's very, very sparse. Now we are going to send the input into this impulse response, and then we are going to see what happened. Okay, and this is called echo filter. But instead of doing that, let us first review what is the convolution first. So the convolution relates the output of a LTI with the input as well as the impulse response. So this is the notation for impulse response. And we now know that this is the notation for convolution. And the answer for convolution is xn convolved with hn to get yn is the same as hn convolved with xn. So order does not matter. You can interchange x and h. What it also means is that the equation can be written in this way: x convolved with h convolved with x. They all mean the same thing. Now, you realize that if either h or x is infinite of length, then you cannot compute yn. Okay, so I repeat. If either x or h is infinite length, so to compute one point, you need to do this infinite for all h or for all x. All right, so it's only possible when x or h is of finite duration. Otherwise, otherwise, you have to use the difference equation. So for example, yn equals to xn plus 0.5 yn. This is a very innocent looking equation, but if you look at the impulse response, what will happen? So we send an impulse into this system, and this system is this guy, described by this. What do you think the impulse response is? Someone, can you help, please? So you say, I do not know. So what you need to do is this. You draw the xn here. Then it is multiplied by 1, right? Because this is 1 multiplied by xn. Then you can get the yn. But you need the second part, which is the 0.5 yn minus 1. So what do we do? So we will z minus 1 here to perform the delay. So we get yn minus 1. So we multiply by 0.5 and we sum. So this is plus and this is plus. Now this guy is now x of n multiplied by 1 plus 0.5 yn minus 1. So we always ask you to draw this figure called direct form 1. Okay, so maybe I should sketch this a little bit better. So this is sum. All right, okay. Now, so of course you'll be wondering what is the impulse response now. So again, by brute force, you can do it this way: time minus 1 x of n. So this guy is 0. We assume that there is no input, right? So this is time minus 1. So what is yn minus 1? Oh, sorry, what is yn? And what is yn minus 1? So we assume that the memory of all this is 0. So it means that output is 0, the memory is 0. Nothing is happening. And since there is no input, the output is 0. Times 0, we get 1. Then the output is, you follow this equation. And then, of course, we get yn is 1, this is 0. So after that, of course, you'll realize that I'm shifting. 1. Now the input is 0. The output is, what's my output? My output is 1, this 1 times 0.5. Now let's try again, 2, 0. So this guy is shifting. So it's now 0.5 square. So you see the pattern now, 0.5 cube. And you realize that although I send a lousy impulse into the system, my h of n is this guy, 1. This is h of n, or I should say also y of n, because this is the output. This guy is 0.5. This guy is 0.5 square, and so on. So h of n is infinite. And if h of n is infinite, and you try to plug into it, this equation, nothing is going to happen, right? You can't even calculate the first point. All right, so the best thing to do is to use this guy. All right. Right, now, what else do I have to do? Okay, so we're happy with this now. And now the other thing which I want to talk to you about is convolution with impulse. So the moment you send an impulse, let us have a system that does this. And 0, 0, 0, 1, 2, 3, 4. 1, 2, 3, 4, 5. Let us assume that my impulse response look like this guy. At time 0, what will happen? In my output, guys, can you all help me? If I send an impulse and nothing else, what will I get? Benedict?
The first one will be a value of 1, is it?
Yes, correct. In fact, I will exactly get the same thing again, right? Agreed? So
Yes.
when something is convolved with an impulse, so we are saying this guy is convolved with an impulse, we get that something. Agree? Now, at time k, I send another impulse. What will I get? What should I get, guys? Benedict again?
So it's continuing to increase when you send the second impulse.
At time k. So k is, for example, equals to 100 index.
So I mean, is the current output going to keep increasing?
No,
Or,
because see?
or is the rest is 0?
Yes.
Then it will be, you start with a value of 1 again.
At where?
Okay.
Correct. So same thing again. So in English, what happened? When something is convolving with an impulse, we get the something at that time. Can you see now? Yes? No? Every time you convolve with an impulse, you get the same thing. Of course, you assume that nothing else is happening here. So now I'm going to try, how about try instead of 1, I'm going to do 3. What will happen to my output? So this will change, right? What will happen?
You will start with a value of 3.
All right, so it's 3 multiplied by this guy. 4, 3. Then second one is what? 6, right? 6, right? Third one is 9, right? Agree? Fourth one is 12, right? And fifth one is 15. Agree? So I'm going to draw for you. This guy generate this guy. This guy generate this guy.
Prof,
Yeah? Yes.
the left side one is called impulse.
This one is the impulse response. This guy is an impulse, right?
Oh, okay. So the left side is called impulse. The bottom one is called impulse response.
Yes, the left one is not the impulse response. The left one is input.
Input.
Is made up of two guys. One impulse at time 0 and one impulse at time 3 delayed by 100. So this equation is 1 delta n plus 3 delta what? N minus?
Minus 100.
Correct. So this guy is called the what? The input, right?
Oh, okay.
This guy is called the impulse, right? This guy is called the impulse delayed by 100 samples scaled by 3, right?
Okay.
This guy is the impulse response of the system, right? This guy is called the output, yes? Can you all see?
Okay.
Okay, so now, if you understand this, so I'm going to do question 3 now. So instead of looking at my code, so instead of the question, I change it a little bit. I have an impulse response that looks like this. What did I do? Can you all think? What did I do? So I'm going to plot the impulse response that looks like this. Okay. So this is, I should change it. X. Okay. I call this the blue line X, the input. Can? The input only have one impulse at time 0, one impulse at time, is it 40? Yeah, and one impulse at time 60. Can? All right, and then what do? I will now send this guy into the system with this impulse response. It goes from 1 to 10 and then 0 otherwise. When I convolve, so now what do? I convolve my X with my X with my, sorry guys, I made a mistake. H, 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 H. Okay, let's run again. So the blue one is my input. The top guy is my input. The blue one is my impulse response. Every time I send an impulse, I get my impulse response. But this guy is negative value of 0.5. So see the output is the impulse response times minus 0.5. And this guy also 0. How many? 3. So it's 0.3 multiplied by this guy. So now if I'm going to, so if the quiz question is like this, what happened if I send 111 into the system at time 1, time 40, and time 60? How would it look like? Can you tell me, guys, before I run the code? Benedict. So these are the quiz question, right? I ask you, and then if you have done the work, you technically you just change your parameters and you just run. What you'll see is you'll see these 3 blue guys happening at time 1 or time 0, time 40, and time 60. Let's run. Right? Can you see now what's happening? So you have to write your code, and the code is only very few lines of code. In fact, the only thing that's really happening is this guy. The rest is plotting. Now, so I'm going to ask you now, what will happen when I do this?
You'll get bigger.
Yes. But what happened at 40?
Nothing.
Correct. So this is the first one. This is the second one. Yeah, that's it. Right. So go and write the code like this. Of course, I'm writing in MATLAB, but you can write it in Python. No difference. So I use convolution, right? Now, so this is a more difficult question. Can you predict what will happen? Hauke,
Yes, sir. Uh, the first one will
will
be
you see two triangle?
yeah. Then the second one will be like times 5 of the input one. Then the last one got nothing.
No, the last one got nothing. The second one overlaps the first one. So on
Oh.
the fifth sample onwards, something is strange happen. You will sum up. Can you see? So it's
Oh.
the first guy and then second guy and then sum together. Okay.
Yep.
All right. So if you can understand this, then we have just done question 3. Of course, very similar idea, and then you can listen to it and things like that. Just now we have seen it. All right. Pause. So in the fourth question, it asks you a spectrogram. So please Google what is a spectrogram first. And a spectrogram is a picture like this. And then this picture on the x-axis is time, on the y-axis is frequency. So it goes from 0 hertz to 10 kilohertz in this example. And here is time. So the colorful thing shows that there is something there, and the black thing shows there's nothing there. Here, it shows that there's some signal at this frequency, at this frequency, at this frequency. So this is actually speech. All right. So what about this guy? So what about this guy? It goes from 0 to 5 seconds, and it shows that there is a signal here. The blue means there's nothing. A red means there's something. So there is something, a signal at 2000 hertz going to 1000 hertz going up again. So in fact, if you listen to this, you'll be going at 2000 hertz, some frequency like low frequency, and go up again, then go down again, things like that. So this picture of a spectrogram shows at time versus which frequency, what sound is there. All right, let us see. So now I'm going to go to my question 3, and I'm going to run this guy. Oops, no, not question 3. I should be question 5 now, the spectrogram. So you'll realize that I have plot from time 0 to time 16,000 samples. So it's 2 seconds, a frequency going from low and to high. Okay, this is from 0 to pi radian. So actually it's going from 0 to, I think, about how many? Maybe 1,000, 2,000 hertz. I mean, you have to go and figure it out. But it goes from low frequency to high frequency. Let me play for you again the sound. Can you hear the sound? So it goes from low frequency to high frequency. I think this is from 0K to about 3K. Okay, so this, then the signal that I'm plotting is called X, or making a sound. So let me show you X. So plot X. Then you say, I'm showing you nothing but 0 to 16,000, 2 seconds worth, because 1 second is 8,000 sample. But let us zoom in. So what you'll see is that if I zoom in from here, you'll see that I'm actually plotting a sinusoid. But if you notice very, very carefully, the sinusoid, although have the same amplitude, is starting to become, the period is becoming smaller and smaller. Okay, Now I show you. So where would things be exciting? Maybe here. You see that from here on the left hand side compared to the right hand side, the spacing is becoming narrower and narrower. So what happened is that it go from low frequency to high frequency. Okay. Now this is called a chirp signal. So if you have no idea what a chirp is, just chirp wiki. A chirp signal is a signal of increasing frequency going from low to high. See, like this. Low frequency and higher and higher and higher, higher. So it goes like this. So with this chirp signal, that's what we hear just now. So what is a spectrogram? You look at this and you can't really tell what's happening. You know that you have a sinusoid of amplitude of 1 and it's becoming faster and faster, but how fast? You can look at the spectrogram. A spectrogram shows time. So this is this figure is wrong. Okay, it should be time here and frequency here. So it's time here, and then we show you that the frequency is increasing. So I run for you again. So it goes from 0 to 16,000 samples at it goes this. Now I'm going to try to do something else. Maybe I'll try 4,000. Let's see what happens. What happened, guys? It went high and it went low and then went high again and went low again. Okay, so by changing the chirp function, I can generate different signals. Okay, so you have to be playing with this, and of course, then you say, "Am I telling you the answer?" By changing my values, the answer changes completely. Okay, guys. All right. So that is the chirp. So that is for question number. This is what is a spectrogram. Examine what is a spectrogram and comment what is a spectrogram. So my last part of the question is this. I have a B and A, okay? And I'm going to show you what is the B and A first, which is like 5 and 2. So I will set B and A first. Okay, I close all, clear all. I set B and A first. And then I do filter tools, B and A. So I know that you do not have filter tool, but go and get MATLAB and filter tool. And when you get a filter tool, you will get something like this. And then please click right hand side and do magnitude first. And then you tell me, what does this filter do in terms of magnitude? Benedict. So this is the lab, right? So immediately you say, sir, the input frequency goes from 0 to pi. The output at 0, 0.1 pi, 0.25 is close to 1. In fact, above 1, 1.05. But at a very interesting frequency, at 0.375, the output is close to 0. Can you see now? In fact, at 0.375 exactly, it is almost 0. Again, so what does the filter do, Benedict? What kind of filter is this?
Band pass, is it?
What does band pass means?
Filters out a specific band of frequencies.
Okay, so look at this. What is band pass? The gain is 1 here. E is 1. At this frequency, what happened?
It passes through.
At low frequency, it passes, right? At high frequency, it becomes 0. So this is called a low pass filter. Can? This guy?
It's the opposite.
Which is?
high frequencies pass through.
So it's called the,
High pass.
yeah. So which one am I showing you?
The band stop one.
Correct. So can you see now? At this frequency passes, in the middle, it stopped. Clear? Now, if I'm going to show you what the filter does in time, what should I do? I'm going to generate one frequency at 0.05 pi. Okay, I'm going to show you one frequency at 0.05 pi and one frequency at 0.375. Yeah, and I'm going to send it to a filter. And what do you think the filter will do? So I'm going to generate a signal x of n that is made up of 1 cosine 0.05 pi n plus 1 cosine 0.375 pi n. Okay, and then I'm going to send it to this system. This system described by that B and A. Correct? What do you think will happen to my output? Ziyang, can you tell me? What do you think will happen? Right. This guy will get cancelled off because his gain is 0. This guy, magnitude is multiplied by 1.05, right? Can you see? At frequency 0.05 pi, he's multiplied by 1.05. His phase is shifted by so the answer is 1.05 cosine 0.05 pi and minus 0.03 radian. That's my output. So my input is this and my output is this guy. Let's see. Okay. All right. So I'm going to generate my input. My input is 0.30. I'm going to generate a signal that is 8,000 samples long. The first frequency is 0.05 pi. The second frequency is 0.375 pi. I am going to have an both signal is the same. Both signal is the same one. Okay, and then I'm going to sum and I'm going to run. So what am I showing you? The green guy is the low frequency signal, 0.375. X sum, sorry, the green guy is 0.05 radian per sample. The blue one is the 0.375 radian per sample. The red one is the sum of the two. So you see, the red one goes up, comes down, goes up, comes down, and it is the blue plus the green. Right. Now, what else do I want to show you? I'm passing through my filter. My spectrogram. I have 0.05 pi, one line. 0.375, one line. The rest of the blue. So my spectrogram shows I have two signals. I'm going to pass through my filter. The red guy is my output. My green guy is my input. You see, my output is slightly bigger than my input. And it's phase shifted by very, very little. My X sum is my original one. So what happened, guys? My output has been cleaning up the dashed lines. My output, even though my dash line was given into my system, I have cleaned it up. I look at the spectrogram. See, the other guy is completely gone. Okay, so let's see the code. The code to deal with this is very simple. I give you B and A. I filter my B and I use my filter B and A on my X sum, and then now I'm showing you my output Y, which is where's my output Y? Here. Okay. Now I'm going to ask you this question now. If I do not, so I now know that my filter create what do you call that? A null and stop at that exactly at 0.375 frequency. What happened? Okay, just think what happened if I, instead of doing it, I do it here. I will change my output to be 0.37329. Okay, 0.37329. 0.37329. So from the figure, I already know that if I'm sending a frequency of 0.37329 into the system, it will become smaller to 0.1. Okay, let's see. Okay, now let's run the guy again. The input is still the green and the blue. The output, sorry, the sum is the red. Okay, looks like before, no difference. Looks like before. The input has two lines, one at 0.05 radian, the other guy now is 0.37329. We send this into the output. Now let's study this carefully. The output is the red line. The input is the dashed red line. Oh, okay, see? So it didn't clean up the signal very well, but it made our signal looking more like the green guy. And now I will show you. So this is the bright yellow line, showing the output. This guy is slightly down yellow line, showing that it has been filtered. Okay, clear? So then you say, did I write a lot of code? No. All I did was to tell you the B and A of the filter, and then one command called filter B and A. You can use Python L filter, and then you can see, and then you can use Python spectrogram. That's it. That's all. The interesting thing, of course, is how to design this filter, which you'll learn in the second part of the course. And of course, now you'll realize that only by changing the input a little bit, right? Just now was 0.375. Something has changed. Okay. All right. Maybe I should convince you by plotting it in different values of plot y, maybe as x dash. So the x dash is all the points that I'm plotting, which is my output. The x cross, I mean. Okay. All right. I'm going to pause now. So with this discussion, I hope that you now can already answer what is number 5. Okay. Now, how do you determine the stability of the system? If you can use MATLAB, Matplotlib, it's easy. What you need to do is FV2 B and A, and you check the pole and zero location. So you see the pole is inside the unit circle, and therefore the system is stable. There's 2 poles here. there is 20 there. Okay. All right. With that, I think I pause now.